you, ma'am.
Dr. Mida, your mic is muted. Your mic is. You can talk now.
Am I audible?
Yes.
Okay. A very good afternoon to everyone. It is my absolute pleasure to welcome you today's keynote session. Before we begin, I would like to request your cooperations in making this an engaging and enriching experience. Please ensure your mic is on mute mode, and I encourage you to take notes and prepare questions for the Q&A session that will follow. Let's make the most of this unique opportunity to learn from one of the leading minds in structural mechanics. Now, let me introduce today's distinguished speaker, Professor Valter Carvelli. Professor Carvelli is a full professor of solid and structural mechanics at Politecnico di Milano, one of Italy's premier institutions for engineering and technology. He holds a PhD in structural mechanics and a master degree in civil engineering. With over 25 years of experience, Professor Carvelli has made many contributions to the field of experimental characterizations and finite element numerical modeling of mechanical performance in composites and related structure. He has worked with prestigious research centers and universities across many countries, broadening his perspective and enriching his research with global insights. He is a prolific author with over 100 papers published in international peer-reviewed journals and has authored a comprehensive book on the fatigue of textile composites. His work spans a range of pioneering areas, including investigating the structural mechanics of advanced textile reinforcement and composites, developing multi-scale models to predict mechanical behavior from micro to macro levels, innovating experimental techniques using three-dimensional digital image correlation, acoustic emission recording, and X-ray microcomputed tomography to study fatigue, impact damage, and more. Professor Carvelli's cutting-edge research has not only advanced academic understanding, but also laid the practical application in engineering. His work embodies a blend of theoretical insights and real-world relevance, which makes him an extraordinary contributor to this field. We are truly fortunate to have him with us today. I welcome our keynote speaker, Professor Valter Carvelli. Professor Carvelli, over to you.
Oh, thank you. Thank you so much for the very nice introduction. And please let me share my screen so I can start with the presentation. Okay, do you see my screen?
Yes, I can see.
Okay, perfect. Thank you. First of all, I would thank the organizing committee for inviting me. It was a great pleasure and honor to be here, and with because it's a very well-known conference with many good contributions that can give an opportunity to have advancement of the knowledge for all of us. I move to my talk of the day that is related to hybrid composite, hybrid laminates. And the reason why we spend a lot of time, me and other colleagues that from KU11 and from Russia, we spent several effort in studying this material because as far as you know, the laminates or composite material are, beside anisotropic, are brittle material. In general, if you want to have nonlinearity or initial nonlinear behavior, you can manage the laminate stacking sequence, but mainly they are brittle. But these have several drawbacks, meaning that you cannot predict, or you do not have any information about the damage that is occurring in the material, and so this is not reasonable in structural application. So we know that from the metal, we can have a different behavior that involves plasticity. So plasticity means that you know where the material is working, and then you can have an alert on the moment where this material is yielding, and then you can have further increase. You can have further increase in the stress that can give us the chance to extend the loading range. So the question is, can we also have some similar plus ductility or ductility similar to the metal in laminate, in fiber reinforced composites, in long fiber reinforced composites? So something that can help us to have an understanding on the evolution of the damage, and then we can also increase, or we can extend the loading above this level. So the answer, according to our understanding and preliminary understanding, is yes, we can, and this can be done thanks to the hybridization. You know, hybridization, there are several ways to prepare to manufacturing hybridization. These three are the main methods. I will mainly focus on the layer by layer hybridization. That is the scope of our work. But you can find in the literature many applications of the other methods. Staying in this layer by layer hybridization methods, there are several work and study that in some way help us to predict the evolution and the behavior of this material, to understand if we could have a chance to reproduce this pseudo-ductility that could be helpful at the application level. There have been a study and model and analytical model that can be used to create this damage mode map that can help us to distinguish which damage mode are going to appear in the material according to the ratio between the two different material we use in the laminate. And so this is very interesting because we know that if we can create a sort of fragmentation in the low strain material, or we can create fragmentation with initial delamination at the interface between low strain and high strain material, this can result in a pseudo ductility that we can observe in the stress strain curve. So this is good preliminary understanding, and then we can use this to select the material, and then moving to see if this is happen in real loading condition. And so this is our aim. We know that if you look in the literature, you have several combination of fibers to create hybrid composite that are mainly listed here. You have few more, but our aim was not to continue in using this coupling, but to exploit if we put together two carbon fiber of different quality. This results in this pseudo ductility, and the main reason for this, that if you can use the same fiber or the same material for the fiber, this will, from one side, enhance the mechanical property because we are using carbon. On the other side, we can reduce the density because of this fiber. And last but not least is the uniform thermal property and electrical property, and so we do not have mismatch in the material. And so this is the reason why some research group work on this hybridization, and this is what I'm going to present you using the same material for the fiber. One fiber have high elongation, one fiber have low elongation, and this help us to create this progressive damage mechanism that leads to pseudoductility. In the past and in the literature, you can find good work related to this all-carbon fiber hybrid laminates that are mainly focused on thin ply, and because the thin ply allow you to create this sequence of damage mode. And so you have quite a number of work on this with thin ply. On the other hand, if you think about thick ply that are more used in the application, you have not so many work on this aspect, and less than for quasi-static test, you have work or study on the fatigue behavior. So our main scope was to extend this knowledge to thick ply of different lamination scheme, and so including also quasi-isotropic laminate, extending our study to quasi-static, but not only, also to fatigue test or fatigue behavior, and then moving to predictive model that can help us to design the laminate according to the peculiar feature of this pseudoductility. And so this is the outline of my presentation that will in some way present an overview of the work that has been done on this thick ply all-carbon laminate, starting from the material feature and then moving to the understanding we had with different loading condition, including the observation of the damage inside the material, and then finally moving to the numerical model that give us this opportunity to predict the pseudo-ductility of this material. As for the material, as I mentioned, we use two different kind of carbon fiber with different elongation at failure and different elastic modulus. Those are listed there, in which this is the high elongation fiber, this is the low elongation fiber. We also investigated the influence of the sublaminate. So what is sublaminate? It's a sequence of pre-preg including these two fiber. In this case, we have high elongation, low elongation, high elongation. And this sublaminate is here in the laminate stacking sequence is mentioned as the orientation. And we investigated also another sublaminate scheme to create unidirectional and quasi-isotropic laminate. And so you see here on this side, which is the thickness that are more frequently used in the application, and the contents of the low elongation fiber in the laminate. This is interesting to understand the final behavior, mechanical behavior of the laminates. Moving to the manufacturing, to understand if the manufacturing have effect on the mechanical behavior, we use both hot press and autoclave with this manufacturing cycle after end layup. And the first step was to understand to assess the quality of the manufacturing, and this has been done with observation with the micro CT to measure the fiber misalignment in the high elongation and low elongation plies. for all the stacking sequence from unidirectional to quasi-isotropic laminate. And what we can see that in terms of fiber misalignment, the manufacturing process does not give huge difference. And mainly the misalignment that is not so relevant is mainly in the high elongation ply. On the other hand, if you look at the void contents that have been measured with images of the micro CT, the void contents that is quite reasonable for many applications is mainly in the in the low elongation ply, in the deep ply. And this is also not so different comparing hot press and autoclave. So from this side, from this aspect, the two manufacturing technique give almost the same quality of the material. So moving to the mechanical behavior. Mechanical behavior, we investigated the quasi-static loading for all laminate and all sublaminate. And the two manufacturing process. We also included the open hole test to assess the notch sensitivity. And then finally at the fatigue loading. Obvious that at the beginning we tested all the laminate I mentioned, and then moving to open hole and fatigue, we reduced the number of material and laminate to because of the material we had available at that time. Anyway, moving to the static test, this is quite standard setup that include the acoustic emission recording, the digital image correlation observation, and also clip extensometer to have measurement of strain both with two techniques. So we put all together. And then this is the final overview of the stress strain behavior in tension, where you can see that what we want to have, that is, this is the schematic on the bottom left, the schematics of what we would have for this material, including the pseudo-ductile stage. We have in the results of the tensile test. What is interesting to observe that obviously the first branch of this curve and when the failure happened in the low elongation ply, and the first branch slope is mainly driven by the low elongation material, which has the higher elastic modulus. Also interesting is to observe that this pseudo ductile range in terms of strain range can be different according to the laminates, the stacking sequence, and also can present different shapes. So here is more flat, here is not, according to the different sublaminates. And this is the reason, and this is a consequence of the sublaminate and the consequence, obviously, of the stacking sequence. But let's go more into detail to distinguish in terms of mechanical property. This is the comparison for both manufacturing process for all laminate in terms of stiffness at the beginning and stiffness at the end of this stress strain curve. And then you can see that, as mentioned, the manufacturing process does not have huge difference between in terms of mechanical property. And as expected, the zero laminate provide higher value for the initial stiffness and also for the final stiffness. And the difference between the two sublaminate is mainly due the increase or decrease of the low stiffness ply in terms of number of ply, and this then give these results that can be also quite reasonably predicted by the typical classical laminate theory. In terms of pseudoductility, or the range of strain where this pseudoductility appears, you can see here this difference. This difference is, as mentioned, this is mainly due to the difference in stacking sequence and the sequence, the difference in the sublaminate. So managing or designing the proper stacking sequence, it helps us to increase or decrease the strain range for this pseudoductility. And this is very interesting because we can in some way design our laminate to have a better pseudoductility or a smaller range for this pseudoductility. That is important from the application point of view. And then this is also visible when we compare the stress at the pseudoductility level, or when this pseudoductility starts, and the final or the final strengths of the material. And this also shows us that changing the quantity and the position and the orientation of the different carbon ply, you can create a smaller or larger gap between the two values. And this is it's very interesting in the application, because you know when you are at this pseudoductility range that you can have further space for increasing the load, and so you can know exactly where your material is working. Moving to the damage, that is the most important part, to understand why we have this pseudoductility and different behavior from one laminate to the other. This is a map of strain at different strain level for the 2-0 laminate with different sublaminate. You can see here that this in the TDT sublaminate, we have a beginning of the lamination, and this delamination slowly grow to cover the complete spacement. If you change sublaminate, this happen, the delamination start, but it does not increase from one position to the entire spacement, but it can appears different position, different beginning of the lamination in different position of the material. And this will give you the difference in this pseudoductility plateau that is much larger than the other, because the lamination appears in different position, and then the evolution is much faster than the first one. And this could be visible also for the quasi-isotropic laminate with this delamination that start and slowly move through the spacement, which is different than the other sublaminate. I would give also a comment on the difference that between this thick ply and the thin ply that you can see in the literature. In the thin ply that I will show you also later in the modeling, you have several fragmentation and the lamination that start at the position of the fragmentation. In this case, that is thick ply, the fragmentation start, and then the lamination at that position start and move progressively through the entire model. So the entire spacement. So it's a slightly different mechanical evolution of the damage between thick ply and thin ply. But finally, what we observed that the pseudoductility of this range of pseudoductility appears also in the thick ply laminate. Moving to some observation with the acoustic emission, this is a recording of the acoustic emission during tensile test compared to the stress strain curve. And then you see that the main difference between the sublaminate is the acoustic recording during the plateau. In this plateau, when the main damage is in the first branch where you have crack in the matrix, then start to have fragmentation, and then this looks to be the time where we have progressive delamination. And this progressive delamination, as I mentioned, is completely different, changing the sublaminate, where in the case of the second set of sublaminate, this is very noisy because it's much faster. You have different position where the delamination starts, and so you can change, or you have quite completely different pseudo-ductility behavior, if this can be named pseudo-ductility. Then moving to the behavior in terms of notch sensitivity, this is quite standard too, the same setup, same measurement technique. In this case, we limit our test to the two quasi-isotropic laminate, and then you see here only the beginning of the plateau. So when this starts, so the first fragmentation, and then the beginning of the plateau in terms of pseudo-ductility. It's interesting to observe the damage evolution in terms of strain map that is quite typical in this case for circular notch, where you have stress concentration at the boundary of the notch. And if you look at the shear strain, it's visible, this distribution. That is the information we have to understand that the lamination is starting at that position. And this happened for the two different loading scenarios that have been shown here. So meaning at the top, at the first fragmentation, and immediately at the beginning of the plateau. And this is quite similar for the other quasi-isotropic laminate, showing the distribution of the strain during loading, mainly at the beginning of the plateau. But what is important is the notch sensitivity, because this pseudo-ductility, or this increase of strain that we can get at this load level, give us the good understanding on the notch sensitivity that I show here, both in terms of notch sensitivity at the stress at the plateau level, and also at the final strength. And then you can see that the notch sensitivity is quite good. We are close to 1. That is, namely, we have the same response of the unnotched material, and this is reasonable, and this is due to this distribution of damage in the more stressed part of the material that allow you to exploit this range of pseudo-ductility, and then to continue increasing the load also at higher strain level. Moving to the behavior in terms of fatigue, we limit our test to the tensile loading, and we limit this test to quasi-isotropic laminate, changing the control of the test. We have some tests with stress control with this 0.1 ratio at 3 different stress level that are from 90 to 100% of the stress at the first peak, so at the very beginning of the plateau. And we have also strain control test with 8 level of strain from the beginning of the plateau to the second branch of the static strain curve. This helps us to understand if the pseudo-ductility can help us to sustain or to have longer fatigue life if or not. Moving to the results in terms of stress control test. This is the range on the static curve, and here is the fatigue life in terms of the maximum stress in the cycle. And then you can see easily that, okay, if we are at 90% of the pseudo at the beginning of 90% of the first peak, we have long fatigue life. We stop at 1 million cycle. But if we approach or you get closer to this stress level, to this pseudoplasticity stress level, the fatigue life became shorter and shorter, and this means that the material does not support or cannot support longer this stress level. This is the reason why for this is that when we get at this level, the fragmentation starts, and then keeping the same stress level, the material have fast evolution of damage, and then it jump to the other branch of the static curve, and then it fail more fast failure. While if you, and this is what in summary is I mentioned, if you look at the evolution of the stiffness of this material or the slope of the stress of the cycle, and then you see that we have very good retention of stiffness if we work at 90% of the pseudo ductile stress, but this will immediately drop down if you are very close or at the stress of the first peak. Contrary to this, we observed for strain control material that we use a much larger range for testing, and so we started just after the first drop, the first fragmentation, and then we also use strain level close to the final failure. And what we have seen that all the strain level we use for test lead to the unfailure to no failure after 1 million cycle, except one that is the highest strain level, very close to the final failure in static loading. And this is very good information because even though you have a reduction of the stiffness that during the loading, your material does not fail and still continues to sustain the load till a relatively high number of cycles. This is motivation, I would say, for this good behavior that is related to this pseudo ductility range we have seen in the static test. The red symbol show the beginning of the stress level at the beginning of the fatigue test, and the blue one showed the stress level, the strain level at the end of the fatigue loading. And so you see that this, when you work in the pseudo ductile range, your material continue to keep the load with higher probably with lower level of stress, and this level of stress slowly move, increasing the strain level and moving to a line along this segment with the slope is the same or similar to the second branch of the material. What does it mean? This means that the material, after the fragmentation of the low strain layer, move or transfer the load to the other ply with high elongation layer, and that continue to sustain the load for longer fatigue life. Obviously, when you are in the second branch with strain in the second branch, this means that you have fragmentation in the low strain layer. You are starting failing some fiber and ply on the high elongation layer, and so this slowly move to shorter fatigue life with final complete failure. But what is interesting that we can exploit this pseudo-ductile range to in some way have good or longer fatigue life, even though we can sustain a smaller range of stress, but your material does not fail completely. And then why this happened in terms of damage mode that we have observed inside the material with the micro CT. This is an observation of one sample cyclic loaded at this strain level after 100,000 cycle. And then so meaning that we are working at this level in terms of reduction of stiffness and strain level. So you see that what we supposed to have is to this fragmentation or crack, intra-ply crack that mainly happen at 45 ply. And then this will gradually and slowly move at the interface. And this is what we expect in terms of evolution and sequence of damage mode. And increasing the number of cycles, this fragmentation will multiply. So you have multiple fragmentation at the same, obviously at the same mainly in the same ply, and this fragmentation is converted to delamination that finally lead to complete splitting of the material and delamination that is after 1 million cycle. But after 1 million cycle, even though you have such a huge delamination here or in another position, the high elongation ply still continue to carry the load, and so your material does not fail completely. The main damage mode that have been observed after 1 million cycle, as mentioned, this splitting in the zero ply. So you have transverse crack that mainly start from the edge. This is almost standard, and also you have crack along the fiber in the 45 ply and starting the bonding. The bonding mainly happen at the interface between 45 and 90 degree 5. This is what we have seen in the experimental test with different loading conditions, with different laminate. Now, our question is, can we predict or can we have a model that can help us to predict this behavior? And then we try to develop a finite element model. It was, in this case, limited to unidirectional laminate because it's the most probably interesting in terms of this pseudo-ductility, and it was limited to quasi-static loading too. What we want to reproduce in the model is the sequence of damage mode that we suppose and that we have seen in the experimental tests. Mainly what we simulate is the fragmentation in the low elongation ply, and these have been simulated introducing transverse cohesive elements in different position at certain distance that was lower than the recovery distance for this material. And we also want to simulate the lamination. So we use cohesive element at the interface between low and high elongation ply. And so what we want to simulate is exactly this damage mode evolution to create this pseudo ductility behavior. And this was performed using a finite element model in a commercial finite element code. In terms of detail, I don't want to go into the detail of the cohesive element damage evolution. That is quite standard. I want just mention that we introduce also the variability of the carbon fiber strength using a Weibull distribution, and this allow us to change the strengths of the fiber that is very well known, assuming this distribution, and so we can create a variation of strengths inside the ply and along the length of the ply. And this is interesting and important because this happened in the real material. Some characteristics of the laminate, so I don't want to read this number because now are not so important, but I'm going directly to the comparison. This is a comparison with a different laminate you can find in the literature in this paper, that is carbon-carbon with a different low elongation fiber than the one I have shown you before, but it was a preliminary model to assess the quality and capacity of the numerical model. And this is the comparison, both in terms of stress strain and in the terms of evolution of damage mode. So in the activation of the fragmentation at different position, and then activation of the delamination at the place where fragmentation happened. And this is quite interesting because it creates, this is the reason why we have this plateau, or we can reproduce the plateau that have been observed in the experiment also with the numerical model. If you would predict also the evolution of the damage, this have been done looking at this movie. Then you see that this is mainly fragmentation. So you have several fragmentation that appears in the material at different position, and this is mainly due to the Weibull distribution, and this is limited to fragmentation with a very small extension of the delamination that is limited at the place, at the position of the fragmentation. And this is what have been observed in the experiment and the motivation for the plateau. Moving to an extended number of simulation. So once we know that the simulation provide good results, that is, we can trust the results, we can extend this simulation to a larger number of laminates, and this has been done. And the main scope to this is to create what we call the damage mode map that we have seen in the very beginning. So meaning we want to give an advice on the different stacking sequence. So if you change the stacking sequence, mainly in terms of low elongation quantity of ply, we can distinguish the damage evolution. So if we have unstable delamination, so the lamination starts very quickly, or if we have fragmentation, then stable delamination that create this pseudactility behavior. And this is the results of this several finite element modeling. Now moving to the sequence I've been shown in the experimental test, including these two fibers. This is the results in terms of stress strain that in some way predict this plateau that is not exactly similar to the experiment. This is mainly due to the measurement of the experimental test and this jump during the first failure. But it's interesting to observe the difference between thick ply, this one, and thin ply, the previous one. In this case, you see that we have start the fragmentation, and then the delamination is much larger and go through the entire laminate. Is not limited to the position of the fragmentation. And this is the difference between thick ply and thin ply, and then finally is the difference between the two pseudo-ductile wave that you can create, changing the thickness and the laminate stacking sequence. Even also for this thick ply laminate, we performed several stacking sequence analysis, and this led us to create or to understand when we can distinguish different damage evolution, and to create this damage mode map. And so having a model like this that can be extended to different stacking sequence with different orientation, this is interesting because in some way we can create this damage mode map, and so we know in the design process of the material which stacking sequence and which contents of low elongation ply can provide us the pseudo-ductile behavior, so meaning then when we can have fragmentation and stable delamination in the material that create this pseudo ductility. So finally, the message is, so this carbon-carbon hybrid laminate is could be interesting material because it's single material in terms of fiber. We can create, and in some way we can control the pseudo-ductility, and further to this, we can also have a model, or we can predict and simulate the damage in this material, having a finite element model like this that can give you also an overview of the damage evolution through the whole volume of the material. So with this, I would like to thank you, and I hope to keep the time properly, and I'm open for comments, or if someone wants to be in contact with me, this is the simplest way. Thank you for your time. You are muted.
I would like to thank our esteemed speaker, Professor Carvelli, for his insightful presentation. His knowledge and expertise have truly enriched our understanding on the topic of all carbon hybrid laminates, tensile behavior, and numerical modeling. Now, this session is open for the question-answer discussion. If anyone have the questions, then please place your questions in the chat box.
Probably we have some in the chat.
Yes. So, sir, the first question is, specific mechanism contribute to the notch in sensitivity observed in quasi-isotropic all-carbon thick ply hybrid laminates?
I would say yes, because this notch sensitivity or insensitivity is mainly due to the sequence of damage mode that you have in the more stressed area. And so this helps you to work in this pseudo-ductile range. And so meaning you can extend, to some extent, you can extend the loading level because your material can experience larger strain in that place. And this is the reason why you have such insensitive or very good behavior of this material at the notch site. I hope this is the answer. The second is?
So our second question is, materials like glass or aramid fibers with carbon fibers in hybrid composites reduces the stiffness of the laminates due to the limited amount of carbon fiber plies. How can we overcome this?
Yeah, you are right. You obviously reduce the stiffness because of the glass or carbon aramid. And this is the reason why I mentioned in the beginning, it could be a good opportunity to use carbon-carbon because we can keep a high level of stiffness, high level of strain because of the carbon, and then you can exploit at the same time this pseudo-ductile behavior. I mean, I do not have a suggestion. If you want to use glass of aramide, you can also have this pseudo-ductile behavior if you properly design the material. But obviously, the final or the initial and final stiffness are lower than the one you can get with the carbon-carbon.
Okay.
So I do not have any suggestion to get at the same level of stiffness you have seen for carbon-carbon if you have glass or aramide.
Okay. Thank you, Professor. Now I would like to thank all of you for your attention and participations. Your presence has made this session a success. I think all your questions have already addressed by Professor Carvelli. I hope that the session has inspired all of you. We look forward to seeing you at our next session by keynote speaker Dr. Binsi Pitt. Thank you.
So thank you for the audience, obviously, and the organizing committee for giving me this chance. I wish you all the best for the remaining part of the conference.
Thank you, Dr. Professor. Thank you. It was a wonderful talk. Thank you.
My great pleasure.
Hopefully, let us meet on a physical mode next time.
I'm